In the rush of the digital world and the silent hum of electric motors, some exhaust beats still insist on reminding us where industrial energy began. Listen closely to the slow, deep thud of an Otto Langen engine block, blended with the sharp, hard-edged impact of iron gear teeth. That is not the sound of modernity. It is an echo returning from more than a century ago. We are standing in front of metallurgy monuments, from the 1869 Otto Langen atmospheric engine that runs purely on air pressure to the Wright R975 radial that once roared while powering Sherman tanks as they ground across European battlefields. Welcome back to the engine history. Today, we slow down to breathe air thick with grease, feel heat radiation from exposed flame, and witness the revival of mechanical legends that reshaped human history. Step back into the 1890s when engine casting hit a brutal turning point. Engineer Herbert Ackroyd Stewart brought the Hornsby-Ackroyd engine to life, the first to chew through heavy fuels like kerosene instead of relying on expensive gas fuel. This configuration uses a heated component, often called a hothead, to force fuel to vaporize before pressure triggers ignition. This is the great predecessor blueprint that laid the foundation for the stubborn compression ignition diesel era that came after. If you respect the raw beauty of cast iron flywheels, love the hard-edged beat of hit-and-miss interruption, and want to help the team preserve engine history on film, please take 1 second to subscribe to the Engine History. Your subscription and support are the pressure line that keeps the team fueled to hunt, crane, and haul these metallurgical heritage blocks back to the shop and onto the load test bench. Hit the notification bell so you don't miss the next mechanical beasts. Stay a moment in front of this 3.5 horsepower Crossley, cast in 1882. This is an artwork from the age of milling and turning craftsmanship. With high voltage spark plugs stripped away, the engineers used a slide valve system paired with an exposed pilot flame that burns continuously to ignite a coal gas mixture inside the firing chamber. This operating method forces the mechanic to intervene directly, dialing in extremely tight clearances. Look closely at the vertical camshaft that drives the valve gear. It synchronizes the open-close timing perfectly for the intake, compression, power, and exhaust cycles of the Otto blueprint. That delicate mechanical tolerance lets small workshops squeeze out torque to drive lathes and heavy pump sets long before electrical grids covered the world. Moving into the early 20th century, we meet a McDonald S-type engine block with a colossal flywheel cast from solid iron. The static mass of that flywheel is the key that creates savage centrifugal inertia, pinning RPM steady enough to pull long, wide, flat belt drives across working farms. Standing as the opposite extreme in stubborn load endurance is the St. Mary's 20 horsepower unit, a true iron beast built to punish heavy duty in oil fields. It operates on the HVID vaporizer cup principle. generated by compression pressure, ignites a small charge in an auxiliary cup, creating the pressure that blasts the main fuel charge straight into the cylinder bore to produce expansion work. With a mass beyond 1,000 pounds, over 450 kilograms, this cast iron block is hard proof of the rock-solid casting engineering of its time. By the late 1940s, diesel compression ignition began to dominate the industrial front. The Enfield twin-cylinder block uses an air-cooled, opposed boxer layout that virtually cancels vibration and delivers an unusually smooth feel for a work engine. Rated at 15 horsepower, it served stubbornly across 2 decades, from dust-choked job sites to marine engine rooms. Next to it stands the McLaren M4MK11, a muscular, multi-cylinder diesel block. Its exposed cast intake and exhaust manifolds display an airflow design that engineers clearly refined compared with earlier generations. That breathing system stays ready to shoulder the harshest load cycles, from driving dynamo generators to powering massive air compressor systems. The peak of mechanical complexity in today's lineup is the Wright R975. This radial engine packs a displacement of up to 16 liters. Although the original design aimed to carry aircraft through the sky, its stubborn toughness turned this aluminum and steel block into the power core of Allied tanks. It produced output up to 550 horsepower, delivering brutal torque to crush obstacles across the battlefield. Closing the formation is the brilliantly colored Lanz Bulldog tractor, carrying tyrannical strength. Its 2-stroke semi-diesel hot-head compression ignition engine is infamous for fuel tolerance, swallowing any burnable liquid, from waste oil sludge to vegetable grease. The slow, sharp, rock-solid firing beat of this cast iron block carved itself into history, working the soil and helping revive European agriculture after the devastation of 2 world wars. These machines do not run on fuel expansion alone. They are also kept alive by sweat and the devotion of mechanical restoration craftsmen. From stripping and reworking open flame ignition on an ancient Crossley, to wrenching and setting tolerances on each one-way check valve so lubrication pressure feeds evenly on a German Charter Gross engine block. When the final exhaust beat fades, the solid cast flywheel still coasts for a long moment on savage stored inertia. Silence returns, but heat and the smell of engine oil still hang in the air. Each quiet rotation is a hard reminder of what human hands could do before the age of computer boards. Thank you for traveling back in time with the engine history to breathe in iron dust and burnt oil. Which impressed you more, flywheel inertia or the compression and fire sound of which engine? Leave your numbers and comments below. See you again on the next historical rotation.